In this lesson, we're going to talk about electronegativity and how it affects the characteristics of a bond. Electronegativity is the ability of an atom to attract an electron to itself in a covalent bond. The higher the electronegativity value, the more closely an electron is held to a particular atom. So if we look at the table below, we see the value for fluorine is 4.0, which is the highest electronegativity, and all the other values are measured relative to that. You do not need to memorize these values. Either you can determine the relative difference based on a trend, or you would be given the table of values. So if we look at the trend, what we see is that fluorine is the highest, and we see that the values increase as we go up the column, and they increase as we go from left to right. So if we compare oxygen, which has an electronegativity of 3.5, to fluorine, we see there's a difference in their electronegativity values. So in a bond between these two, the electrons will be held more closely to the fluorine. But even if we didn't know the specific values, we know that they're different elements, and that based on the periodic trends, we know that oxygen is going to have a lower electronegativity than fluorine. So using these electronegativity values, we can actually determine what's called the polarity of the bond. So we gave in the previous slide the example of oxygen and fluorine, that the electrons will be shared unevenly between them, that the electrons will be held more closely to the fluorine atom because it had a higher electronegativity. Now when we look at an example here with hydrogen and fluorine, we know that based on the trends that fluorine is a higher electronegativity value than hydrogen, and so the electrons are going to be shared unevenly. Now we represent this in a couple of different ways. One, we show the lowercase delta with a minus sign for the more electronegative element, and we show the lowercase delta with a plus sign to show the less electronegative element. And what this represents is that more electron density is being held closer to the fluorine than the hydrogens. So these electrons are being shared unevenly. And when we have electrons that are being shared unevenly, we say that that bond is polar, that there is a polarity to that bond. We can also represent this by drawing an arrow, and the arrowhead points at the more electronegative element, and we put a plus sign on the end of the arrow, and that shows us the less electronegative atom, and also shows us that that is the partially positive charge of the hydrogen in this case, and the fluorine is the partial negative charge because there's more electron density around the fluorine than around the hydrogen. So one way to think about polarity is to think about a tug-of-war match. So imagine we have a group of soldiers and a group of kids competing against one another. Who's going to win this if everyone plays to their full ability? So hopefully you got soldiers would win because clearly they're bigger, they're stronger than the small children. And this is what we can think about when we look at polarity. So when we think back to the example with the HF, the fluorine was relative to the soldiers. It had a higher electronegativity, it was pulling harder on those electrons. The hydrogen had a lower electronegativity, and it was more like the kids. They were not pulling as hard on those electrons. So as a result, the electron density, where the electrons kind of live the most, is around the fluorine, and that gets us that partial negative charge on the fluorine and a partial positive. But remember, these are in covalent bonds, so we only get partial charges, not full charges as we would get in ions. Now, like many things, we see a spectrum of polarity. And what that means is that just like a rainbow gradually changes from red to orange to yellow and so on, we see the same thing with polarity. These are some approximate cutoffs that we will use to distinguish between polar, nonpolar, and ionic compounds, and these are based on difference in electronegativity values. However, we would need the table of electronegativity values to do these calculations and to base it on this table. For the most part, your differences in electronegativity are going to be based on what we've already learned about covalent molecules, so two or more nonmetals. There are different elements but relatively close to one another in the periodic table, so they have a smaller difference in electronegativity. Then we see an ionic between a metal and a nonmetal, where we have a very large difference in electronegativity. So our polar covalent have small differences in electronegativity. Our ionic have large differences in electronegativity, and we also have substances that are what we call nonpolar. And the most common types of nonpolar substances we see are atomic molecules, so something like H2 or N2. Since they're the same element, they have the same electronegativity value and therefore have zero difference in electronegativity. There are some other exceptions where the values are very close together, but without the actual table of values, we cannot predict those substances. So let's look at some examples with the actual numerical values for electronegativity. So our first example is with silicon and phosphorus. And I look, based on our periodic table, I can determine that I have silicon and phosphorus are these two elements here. And what I notice is that the difference in electronegativity value, so 2.1 minus 1.8 equals 0.3. And so this would fall into the non-polar region because it's less than 0.4. When I look at H2 or HH, I don't really care about what the actual electronegativity value is because I know it's the same element, so therefore this has to be non-polar because there's a zero difference in electronegativity. For carbon, which is here, and oxygen, which is here, I notice there's a difference of 1.0, and that falls into the polar or polar covalent region of the polarity scale. And then I look at NaCl, and what I see here is sodium. It's right there, so that's 0.9. And chlorine is here, so that's 3.0. That's a difference of 2.1. And so we see that this is actually ionic. So which one of these bonds is polar? Well, ideally, you would have recognized that HH and FF are both nonpolar because of the same element. And then we're down to looking at CS and NO. Now, without the table, this will be very challenging to do. And in fact, I don't expect you to be able to distinguish between these unless you had the table of values. Because there's an interesting example here. If I look at carbon and sulfur, even though they're separate from one another on the periodic table, they happen to have the same electronegativity value. And again, you would have to have the table of values to determine this, which means we have a non-polar substance here. So when I look at nitrogen and oxygen, which are here is nitrogen, there is oxygen, I get a difference of 0.5, and so that's going to be a polar covalent compound.